Here, we'll dive into our two flagship line array products, Anya and Anna. The first consideration in the design of Anya began with how to address the high-frequency section. Using 1, 2, or 3 large format compression drivers was simply not going to provide enough granularity to properly manipulate the very short wavelengths we would be dealing with. We needed extremely small devices that would have acoustic centers that were very close together. On top of that, we would still need output that would be useful for high SPL. Calculations showed us that a ribbon of 1-inch spaced outputs was needed to accomplish these goals. A horn was developed that created a 1-inch spacing between high-frequency cells for the entire length of the array. Engineering designed a system of staggered apertures creating 2 lines of components to reduce the center-to-center spacing to 1 inch, allowing for extremely precise directivity control. EAW developed a new neo-magnet structure for high-frequency drivers that allow for very high motor strength in a compact package. We also created new tooling to build a structure to be integrated with companion drivers, what we call the engine or manifold pictured here. The result is a staggered 14-element source of 35mm voice coil, aluminum diaphragm high-frequency drivers with high output, high power handling, and excellent sound character. Using smaller high-frequency devices is fundamentally better for extreme high-frequency reproduction. The absence of diaphragm breakup modes and large phase plugs improves the driver's impulse response. Smaller drivers also let us use our preferred diaphragm material, aluminum. We prefer this material because of its inherent internal damping and warm sound. Larger drivers are inherently more susceptible to breakup modes and increased distortion. Like Anya, Anna uses a similar high-frequency section. In fact, it's identical with the exception of the number of high-frequency devices. Anna has 8 high-frequency devices versus the 14 on Anya. We use the same transducer on both products. Anna also has 1-inch spacing between elements. Like the high-frequency drivers, the mid-range device size was driven by the requirement to control directivity over the entire bandwidth of the device. 6 closely spaced 5-inch mid-range elements provide the appropriate spacing and couple with the high-frequency and low-frequency drivers to produce a coherent wavefront. Placing the mid-frequency drivers to either side of the high-frequency section allows for the ideal horizontal spacing to maintain ideal pattern control within the horn and acoustic symmetry across the horizontal plane. But it does place cone transducers within the large format high-frequency horn. This presents 2 familiar challenges. First, the impedance of the horn acts as a low-pass filter on the mid-range, preventing it from combining smoothly with the high-frequency section. Second, the cone transducer geometry dramatically disrupts the horn in a manner that simple features like slots do little to repair. Fortunately, EAW has patented technologies that directly address both challenges. The radial phase plug, first developed for the KF750, optimizes the loading of mid-range, thereby improving the mid-frequency high-frequency transition. Concentric summation array (CSA) technology, first applied to the coaxial device in the AX series, minimizes and randomizes the size, shape, and location of the mid-frequency apertures to present minimum impact on the high-frequency wavefront and optimizing the transition. The technology works on the premise of the 80% fill rule. Ideally, the high-frequency wavefront travels along a solid surface, but that does not help us to integrate the mid-range into a common horn throat. Testing revealed that as long as the high frequency sees a continuous surface that is at least 80% solid material, the impact to the high frequency wave is minimized. As the high frequency wavefront exits the compression drivers, and as it makes its way across the baffle, cutouts open and close in the diamond-shaped pattern so that as one group of diamonds open, another begins to close. This method guarantees that the high frequency will see no less than 20% of the solid surface as it passes over the entire face of the horn. Cutouts that present greater than 20% will create reflective and modulated interference to the high frequency. The mid-frequency driver in Anya uses as strong a magnet structure as the 5-inch frame can carry, driving as large a coil as can mate to the cone. The result is a device with extremely high output potential for its size. 6 mid-frequency drivers were chosen due to the packaging and spacing based upon bandwidth needed to match the 35mm compression driver. 5 inches was also chosen over going smaller due to the low frequency bandwidth. Now on to Anna. Anna uses the exact same CSA technology used in Anya. We are also using the same 5-inch devices found in Anya, as you can see here. Like Anya, Anna utilizes a radial phase plug to improve the loading of the mid-frequency devices to the horn mouth. Anna uses the same 5-inch drivers as Anya, spaced as close together as possible. The only difference is that there are only 4 5-inch devices, rather than the 6 we have on Anya. Taking a look at the low frequency now, offset apertures are used. Anya's low frequency section is based on a dual 15-inch design. The key here is horizontal spacing. The lows needed to complement the mid and high frequency elements and extend horizontal pattern control as far into the base region as possible, but the enclosure also had to pack efficiently into a truck. The engineering team created base apertures that are offset several inches wider than the transducer spacing. This extended the uninterrupted surface area of the horn, but also pushed the apparent acoustic origin of the low frequency sources further apart, making the section wider acoustically than it is physically. This delivers consistent, symmetrical horizontal directivity and transitions effectively to the pattern control of the mid-range. Like Anya, Anna features offset aperture loading of the low-frequency transducers. Again, this means that the apparent acoustic origin of the low-frequency devices is wider than the physical spacing. This provides improved low-frequency pattern control and integration with the mid-frequency beam width. For Anya, the 15-inch woofers utilize a 4-inch voice coil with a 32mm coil winding and a plus-minus 12.5mm linear travel range. In short, it's one of the most capable 15-inch woofers available to deliver the high impact and SPO we needed. Anna's 10-inch low-frequency woofers are just as high-powered for their size. Despite having two 15-inch or 10-inch woofers placed within the enclosure, the horn of Anya and Anna fills the entire face of the enclosure. By minimizing and dispersing the openings for the low-frequency energy, they become essentially invisible to the mid-high energy. This helps achieve excellent pattern control in the horizontal plane. Now let's take a look at the entire acoustic package. Each Anya module contains 22 devices, requiring 22 channels of signal processing and 22 channels of amplification. Each Anna module contains 14 devices, requiring 14 channels of signal processing and 14 channels of amplification. The audio network and bidirectional communications are on the Dante platform from Audinate. Anya and Anna are possible only because of the major leaps that have been achieved in DSP, amplification, and networking in terms of speed, power, and size. There's an IR transceiver in each of Anya and Anna's faces, so when you first connect to a network system, the arrays are already self-aware of their physical configuration. The only thing you have to do is tell the software which is left and which is right. If there's a failure during a show, the system will report back to your connected software that there has been a problem, and Resolution will show you where that problem is, and will also offer you an array recalculation to heal around the problem. This can be uploaded to the system without any pops, clicks, or gaps in the audio, but it's still the user's choice whether to go ahead or just continue without changing parameters. Just as a general point, any system changes, even those that need a complete reconfiguration, can be uploaded in 3 to 4 seconds. This is without any break or pause in the audio. For example, you are covering a main floor only, and the show was oversold, so they opened the balcony. You adjust the coverage to include the balcony, and it will now be included. This is done entirely through software without any physical changes to the array. Let's take a quick tour of the back panel. Power is utilized via PowerCon True 1 connector. Power is utilized via PowerCon True 1 connector. Dante, analog, AES, and EBU signals are accepted. There's an Input Selections button, a test button that searches for faults when pressed, and a network activity indicator. Both Anya and Anna have unique flybars. Each Anya and Anna flybar has been designed at our standard 10:1 design factor and is capable of supporting 18 enclosures on a single unit. This may sound like a lot of weight on a single flybar, but bear in mind that the predominant stress that the Anya and Anna rigging sees is shear. Line array rigging must be designed to withstand both shear and lever stresses when physically curving and/or tilting an array. The flybar offers 3 options to pick it up from 1, 2, or 3 points, but you never have to calculate which pick point will give you the right up or down angle. Pictured above is the Anya flybar. And here's a look at Anna's flybar. Even though users can't see the rigging, we have multiple failsafes to ensure complete engagement. If the rigging handles can be driven all the way home, it guarantees the rigging is fully engaged. If any part of the rigging doesn't align internally, the system won't link together and the handles won't push home. The rigging system is accessible for inspection or service by removing the side panel of the enclosure. Routine inspection of rigging components is always a good idea, no matter what equipment you suspend over people's heads. Before we move on, let's briefly review differences between Anya and Anna. Note that Anna is very similar, but in a smaller package and wider horizontal pattern. Let's take a moment to look at these lists. Now, I'll look at the Otto subwoofer. Otto offers dual 18-inch woofers, and energy exits the cabinet through 4 apertures, one in each corner. These offset acoustic apertures allow Otto to be placed in any orientation and allow energy to be directed in any direction, depending on the needs of a particular application. The offset apertures also mean the apparent acoustic size of Otto is larger than its physical size, just like the LF drivers in Anya and Anna. These offset apertures also aid in the enclosure's ability to do standalone cardioid and hypercardioid patterns while minimizing harmonic distortion. It works as a low pass. Frequency response is optimized for the enclosure, allowing a broad crossover range. Classic cardioid, hypercardioid, and end-fire arrangements are easily produced from even a single module. Here are a few bullet points to highlight the rigging capabilities of Otto. There's captive rigging, similar to Anya and Anna. It interlocks in both the X and Y planes. IR sensors on all sides identify array configuration. This particular system rigs standalone, meaning it does not conjoin to Anya or Anna. The power plant for Otto is based on the Anya and Anna power plants, so most features are familiar to existing adaptive product owners. The power plant is fan-cooled, providing reliable operation in hot temperatures, range 0 to 45 degrees Celsius. 1700 watts of PowerSoft D-Class power are provided to each of the 2 18-inch drivers. The power connection is via Nutric True 1 connectors rated for 20 amps. The onboard battery-powered test feature is also used on Otto. One push of this button confirms no errors were logged on the last performance. The function button allows for input selection and for internal features such as adaptive bypass. Inputs include primary and secondary Dante network ports, analog, and AES loop-through for analog. AES can be applied to a single enclosure, while Dante handles the distribution to the rest of the enclosures. Let's take an overview look at Otto. There's 2 18-inch components using EAW offset aperture loading. It's self-powered with PowerSoft amplification. Operating range is from 22 Hz to 160 Hz. The coverage horizontally and vertically is adaptable. Calculated output unadapted is 130 to 136 dB, and half space loaded 136 to 142 dB. Now that we're more familiar with the products, let's take a closer look at how it all works.